Hi, today we'll study briefly about F distribution. So R.A. Fisher is very famous statistician who essentially built the foundation of statistics. So one of his contribution is developing ANOVA, analysis of variance, and so that uses F distribution. That's one of his main contribution. The density of F distribution is a little bit complicated, like some kind of a ratio here, and the random variable y is supposed to be positive. So to understand this F distribution, the derivation. So this is more like a definition of the F distribution rather than a theorem. Three conditions. So first one is U is random variable with chi-square. So U is chi-square R1 and V is another chi-square R2, and these two are independent. Then the ratio, so expectation of this guy, right? Expectation is equal to 1 because the expectation of U is R1, so divided, and so here the expectation, so what is the, let's actually compute, so this one, the denominator also the expectation is equal to 1, but the ratio itself is not, so if you can, they are independent, right? So U R1 times R2 divided by V, and U is chi-square R1, and so the expectation of U is R1, and what is the expectation of V1, V inverse? So so remember that if X is a gamma alpha beta, the expectation of a, right? I covered this in the class. So I think this is alpha something like that. Sorry. Okay. Beta. Okay. I have to check. But let's assume that this is true. I will, well, okay. Let's do it again. So what is the expectation xk? This is xk. 0 to infinity. So that is beta over x dx, right? So that's basically, this is a PDF over gamma plus k beta. So we can actually, if you use, the integration supposed to be alpha plus k. That is okay. Okay, so beta k. So it's not correct. This is beta k. So that applies. So and then here V is chi-square R2, which is gamma 2 over R 2 alpha over 2 and beta 2. So then expected value of V inverse is gamma 2 over R2 plus minus 1 R over okay equal using the formula gamma 2 of minus 1 times 2 to the minus 1. So that is 1 over R2 divided by 2 minus 1 times 2 over 1, which is R2 minus 2. So that is 1 over R2, right? So that's, I think we already covered this before, but anyway. So that is the F distribution. So actually that is the variance. Recall that that is the variance of the T dis, right? T random variable with the degree of freedom R2. Okay, so that's exactly true because the T is what? The T is C given square root of V divided by R. So if Z T square, then Z square divided by V divided by R. So that is Z square is chi square 1. So divide 1, right? This is chi square 1. This is chi square R. And we divide by their corresponding degree of freedom. So it's n here. Okay. So how to derive this? Well, so this is chi square R1. So chi square R2 and independent. So we can obtain the joint PDF. This is joint PDF of chi-square, two independent chi-square distribution. And then because we have x defined to be something like this, and so we have y defined to be another one. And then this is fairly straightforward transformation. And the inverse transformation is this, right? This is easy to check. And the Jacobian of the inverse transformation becomes R times R y times R1 divided by R2. So basically, we really don't care about constant. What we do care about the functional form inside U and V. So here U is a kind of polynomial, right? And then exponential. So that we can apply directly. This is U. Oh, okay, sorry. So this is, the whole thing is U, right? And this one is V. And this is Jacobian. So that's the Jacobian of the inverse transformation. And so that we just simply apply, this is the U part, this is the V part, and simply apply corresponding degree of freedom, and then exponential term inside, because U times V, U times V, U plus V, right? U plus V here. So this is a U plus V. It becomes something like this, and this is Jacobian, and then from that we can easily take so question is, how do you compute? So if you just look only, so it's a constant, right, times y. So if you look at this 2 over R2, R1 plus R2 minus 2, and here we have y, so minus 1. And then exponential minus r1 divided by r2 x times y dy. So what is the value of the integration inside? I mean, ignoring the constant. So this one becomes equal to, this is basically PDF the functional inside the gamma alpha beta, where alpha equals to r1 minus r divided by 2, r2 divided by 2, right? And beta equals to what? R1 minus r2 x divided by 2 inverse. So that, right, that is the okay. So what is, recall that PDF of alpha beta is what? Gamma alpha beta is y alpha minus 1 e minus beta y, right? Or x, whatever. So since we write it, y divided by beta, and so there is constant. So that's exactly, so that means this one, if you do integration, that is beta times beta alpha. So that, and using this, right? So which is gamma r1 divided by r2 plus r2 divided by 2 times 1 over r2 divided by r1 x divided by 2 to the minus alpha. Minus alpha is this. So you can simplify the integration. So that gives the justification for the derivation. And now what is left is this property. One of the property is where this is x is what? X is u divided by r1, v divided by r2, u is chi-square r1, v chi-square r2. Independent. So the inverse, x inverse is v divided by r2, right? So u divided by r1. So that's an independent. So that's basically follows F distribution with change the r2, r1. Another interesting property is 1 over 1 plus r1 x. So what is x? X is this one, right? So okay, sorry. X is here, r2. So basically we can, if you multiply r1 divided by r2 times u divided by r1 v divided by r2. So everything cancels out. So this is this is what? V divided by u plus v. And v is v, what is v? V is chi-square. So recall that v is chi-square r2, which is gamma 2 over r2, right? And u is chi-square r1, which is gamma r1 minus 2. So that means this one is beta distribution with numerator, the degree of freedom for numerator is r2 divided by 2, right? So that's so using the definition of beta distribution,